Some vehicles operate with conservative pressure caps that lower the boiling point of coolant intentionally. Under real driving conditions, this creates earlier heat soak. As technicians encounter more of these cases, a question keeps coming up. Why do so many cars feel restrained even when diagnostics show nothing is wrong? Vehicles arrive with clean scans and no obvious faults, yet their response doesn't match what the data suggests. That gap between what the engine reports and how it behaves is where these cases begin. Throttle response is slower than expected, not because the engine is weak, but because its output is being managed conservatively. Acceleration arrives with hesitation, not as a mechanical delay, but as a result of how the system decides how much response to allow. The restraint isn't accidental. In cases like this, the behavior remains consistent because nothing is actually failing. One shop documents a case involving a crossover with moderate mileage. The owner complains about sluggish highway merging. Diagnostics show ignition timing pulled back more than expected, even though fuel quality is good and operating temperatures are normal. Under those conditions, that behavior doesn't make sense. The reason only becomes clear later when the timing maps are examined more closely. The timing maps are conservative by design. They're written to accommodate worst-case fuel quality, emissions margins, and knock prevention under extreme conditions. In everyday driving, that margin is never used, but it's never released either. When timing is optimized within safe limits, throttle response improves immediately. Torque delivery feels more linear. Fuel efficiency often increases slightly because combustion is more complete. Nothing mechanical changes, no components are upgraded, and the engine is simply allowed to operate closer to what it was already capable of. This is why timing adjustments are one of the first things tuners touch, and one of the first things manufacturers lock down. The difference isn't subtle, which is exactly why it's regulated. In another shop, a vehicle with no overheating history shows the same restrained behavior under load, even though coolant temperatures remain well within normal ranges. Most drivers assume cooling exists solely to prevent overheating. In reality, cooling systems directly influence performance. As load increases, the ECU begins reducing output earlier than expected. At these temperatures, that intervention should not be necessary. This happens long before the temperature gauge moves. Some vehicles operate with conservative pressure caps that lower the boiling point of coolant intentionally. Under real driving conditions, this creates earlier heat soak, which triggers protective behavior sooner than necessary. When system pressure is optimized correctly, thermal stability improves. The engine maintains normal behavior longer under load. Performance doesn't spike, it stops dropping prematurely. Again, this is not advertised, it complicates warranty exposure. Fuel delivery follows the same theme. Factory fuel pressure is set for emissions consistency, not atomization quality. Lower pressure reduces injector noise and stress during testing. Under acceleration, however, fuel dispersion suffers. As combustion becomes less even, throttle response dulls slightly, and the ECU compensates by adding more fuel, which increases deposits elsewhere over time. Adjusting fuel pressure improves spray pattern and combustion stability. It also alters emissions behavior just enough to cross regulatory boundaries. That's the trade-off. As technicians move downstream in the exhaust, restrictions become more obvious. Exhaust systems are designed around noise compliance first. Flow comes second. Baffles, chambers, and resonators smooth sound, but they also introduce back pressure. At lower RPM, this rarely matters. At higher RPM, it limits efficiency. Removing restrictions improves flow and response. It also increases noise and violates regulations in most regions. The power gain isn't the result of anything exotic, but of basic mechanical logic since engines function as air pumps. Restrict the outlet and the pump works harder for less output. Manufacturers choose quiet and compliant. Performance becomes secondary. Crankcase ventilation systems quietly undo more than most drivers realize. To meet emissions requirements, oil vapor is routed back into the intake rather than vented. Over time, that vapor coats intake surfaces, sensors, and valves. Heat turns residue into carbon. Engines adapt continuously over time, adjusting their behavior even when no physical failure is present. Idle control begins compensating automatically, fuel trims shift to maintain stability, and throttle opening increases gradually, allowing the driver to adapt without noticing the change. Installing oil separators reduces contamination throughout the intake system, which helps maintain sensor accuracy and keeps combustion behavior stable over time. These devices are often labeled for off-road use only, not because they damage damage engines, but because they bypass emissions routing. Transmission behavior tells a similar story. Manufacturers advertise sealed systems and lifetime fluids, but automatic transmissions generate heat and debris continuously, causing fluid to shear, additives to degrade, and clutch material to circulate through the system. Early symptoms tend to be subtle, usually appearing as hesitation, delayed shifts, and increased heat under load. Partial fluid replacement restores friction characteristics without shocking the system, which improves shift quality, stabilizes operating temperatures, and extends overall longevity. Dealerships avoid this approach because it contradicts lifetime claims. Independent shops rely on it because it prevents rebuilds. The transmission doesn't become stronger. It stops operating on degraded fluid. Electrical grounding is one of the least discussed factors, yet one of the most impactful. Modern vehicles rely on clean reference voltages. Sensors report data based on stable grounds. Over time, corrosion increases resistance at grounding points. Signal noise creeps in. The ECU doesn't see failures, it sees inconsistent data. As signal quality degrades, fuel trims begin to wander, ignition timing varies slightly, and throttle response becomes increasingly unpredictable. Cleaning and restoring ground paths stabilizes sensor readings. The improvement feels disproportionate to the effort because the entire system depends on electrical accuracy. This is rarely addressed during routine service because it doesn't fit replacement-based diagnostics. Tire pressure provides a more visible example of conservative calibration. Door jamb pressure values assume full passenger loads, cargo, and long-distance comfort. Most vehicles are driven lightly loaded. Lower tire pressure increases rolling resistance, which dulls steering response and slightly reduces acceleration. Adjusting pressure to match real usage improves efficiency and responsiveness. It also alters wear patterns and ride characteristics, which manufacturers prefer to standardize. The vehicle itself hasn't changed, but the assumptions used to calibrate it no longer match how it's being driven. In several cases, the only place the restriction exists is in software, even though all monitored systems are reporting normal operation. Modern ECUs monitor emission systems continuously, and as behavior approaches regulatory thresholds, performance is reduced preemptively through softened throttle response, retarded timing, and richer fuel mixtures. These adjustments protect compliance, not hardware. Disabling those monitors removes the constraints, allowing performance to return without triggering fault codes, even though the vehicle appears to operate normally. This is where legal boundaries are crossed, not because engines are being harmed, but because certification requirements are being bypassed. Fines reflect that reality. Seen together, these behaviors point to the same underlying constraint, where the hardware is capable of more than it is permitted to deliver. In each case, the components are doing what they were designed to do. The limitation comes from how tightly their behavior is being controlled. The so-called illegal tricks aren't secrets so much as responses to imposed constraints, ranging from maintenance practices delayed too long to calibrations locked down for reasons unrelated to durability. The reason they feel dramatic is not because they add something new, but because they remove something artificial. Once that's understood, the way cars age looks different. A vehicle that feels slow isn't necessarily wearing out. It may simply be operating deeper inside boundaries it was never meant to push against forever. That's the difference between failure and restriction, and once you know how to tell them apart, you stop chasing parts and start questioning limits.